Start speaking in English. Okay, I'm going to go live now. Just a second. Okay, I think we're live now. So hi everyone, thank you all for being here. I see that we have a great number of people, so that's good. Today I have the honor to introduce you to Juan Maldacena from the Institute for Advanced Studies. Let me give you a little background about Juan. He did his undergraduate studies at Universidad de Cuyo. Then he obtained his PhD at Princeton University to then hold a postdoc position at Rutgers University. After that, he became a faculty at Harvard University, and now he is a Carl P. Feinberg Professor at the Institute for Advanced Studies. Some of his fields of interest are string theory, general relativity, the large and limit of gauge theories and gravity, cosmology, and quantum gravity. Today, he's presenting about the entropy of Hawking radiation. So thank you, Juan, for accepting our invitation. Feel free to start your talk when you're ready.
Okay, so I'm ready. So thank you for the invitation. It's a pleasure to be there virtually. And please ask me questions during the talk, interrupt me with questions. So don't wait till the end if there is something you want to ask or some comment you want to make. So my talk will be about some new results on the entropy of Hawking radiation. So black holes have been in the news recently through many different observations, from collisions of black holes to the picture of the black hole at the center of the M87 galaxy, as well as stars orbiting the black hole in the Milky Way galaxy. So we are in the golden age for experimental black hole observations. But our talk will not be about these observational aspects of black holes, but will be about the quantum aspects of black holes. So aspects that have not been observed, but are interesting for theoretical reasons. So in particular, we'll discuss some recent progress on the black hole information problem. So the outline of the talk is that first, I'm going to remind you why the black hole entropy is the area of the horizon, why we assign to black holes an entropy. Then we'll discuss a new notion of entropy that involves the so-called fine-grained entropy that is also computed via an area formula, except that it's a slightly different area. And then we'll discuss how to apply this formula to compute the entropy of radiation coming out of black holes. And the final conclusion is that we will get a result that is consistent with information conservation as opposed to information loss. Now, this talk will not be historical, but hopefully it will be pedagogical. So the black hole, as seen from the outside, can be described by this metric. So this is the famous Schwarzschild solution. There is a Schwarzschild radius given in terms of the mass and so on. And so that's how we describe the black holes classically. Black holes are the important point when you consider quantum corrections is that black holes have a finite temperature. So a temperature proportional to 1 over the radius of the black hole. That's for the Schwarzschild black hole. Now let me try to give you an argument for why there is this temperature. So the argument is that we can have, the argument is the following. So imagine that, forget about black holes for a second. Imagine you have a thermal partition function. So you have a thermal system, could be, let's say, a quantum mechanical system. Then you can compute the thermal partition function by taking the trace of e to the minus beta h. This is just the definition of the thermal partition function. And this has an alternative point of view, so we can view it in a slightly different way, which is that we can think of beta, instead of the inverse temperature, as some amount of evolution in Euclidean time. So if we had here e to the minus ith, that would be the unitary, just the unitary operator that does evolution in ordinary time. But if we change t to I beta, then we have evolution over Euclidean time, okay? And then we're taking the trace, and taking the trace is somewhat similar to making the system periodic in Euclidean time. So the partition function can be viewed as path integral where we make time Euclidean and periodic with length beta. Okay. So, so in other words, the theory on an Euclidean circle is related to a system in thermal equilibrium, where the temperature is 1 over the size of the Euclidean circle. Now, then we can go back to the black hole metric that we discussed before. That's the original Schwarzschild metric. And then we can make time Euclidean. So we get a new metric. So we get this metric. So this is a metric where the signature is Euclidean, so all plus signs in the metric. And here now we see that where the horizon was before, now again at RS, this factor in the metric is shrinking to 0 size. And it is possible to adjust the period of time here in such a way that this circle shrinks smoothly. So in other words, if we adjust the temperature to be some specific number, which actually turns out to be 2 pi Rs. So that comes from looking at these two terms in the metric and making sure that the size of the circle is such that the metric shrinks smoothly here at where the horizon was. Now in Euclidean space, you have a completely smooth surface like that looks essentially like the origin of the Euclidean plane. So, and where the time direction is the angle around the center of the Euclidean plane. So this intends to be a two-dimensional picture showing the time direction and the space direction and the radial direction, forming a geometry that looks a bit like the geometry of a cigar. So imagine a little cigar here at the tip of the cigar. We have a perfectly smooth metric. Okay, so that's what the Euclidean black hole is. And we discussed before that if we have a Euclidean theory with a circle that is periodic, we can think of that as a thermal theory. So Gibbons and Hawking interpreted this solution, this Euclidean solution, as telling us what happens when, well, as a solution describing a black hole in thermal equilibrium with a gas of particles outside. And at temperature beta equal to this value, which is just the inverse of the Hawking temperature, which Hawking computed in a different way. But this is what I'm telling you here is probably the simplest way to understand this formula for the temperature. Now, once you know the formula for the temperature, you can use the first law of thermodynamics, which tells you that ds is equal to dE over T. And since we know E is equal to the mass of the black hole and we have the temperature as a function of the mass, we can integrate this formula and find that the entropy turns out to be equal to the area of the horizon divided by 4g Newton and h bar. So I'm setting here h bar, the speed of light, and the Boltzmann constant to 1, but all those constants of nature also appear in this formula. And so the combination that you have here in the denominator, it's a length, sometimes called the Planck length. So in nature, that would be a length of order 10 to the minus 33 centimeters. And so that's the formula for the entropy of the black hole. So this length is so small that any macroscopic black hole has a very, very large entropy. So in fact, if you attempt to compute the entropy of the universe, of our observable universe, the entropy would be, well, there are different contributions, like, the entropy of the CMB, the gas in the galaxies, and so on. But most of the entropy would be in the supermassive black holes at the center of the galaxy, because this factor would be so big for them. Now, perhaps the most surprising aspect of this is that the black hole is a thermodynamic object, and this is surprising because it looks like it's just a single solution of the equations. Now we'll discuss now in more detail the geometry of a black hole. So the geometry of a black hole.
Can I ask something already? In this picture you showed before, the cigar, this is valid only for the exterior of the black hole, or
yes. So this here we well, all that we've done here is to consider this Euclidean metric. metric. And then we interpreted the Euclidean metric as telling us, telling us what the partition function, computing the partition function of a black hole in thermal equilibrium. And if we do computations here, like expectation values of operators, if we have quantum fields and so on, we can also do that. And indeed, as you are saying, those would give us those expectation values outside the black hole. They're not telling us anything about the interior for the moment. But we'll start discussing the interior very soon.
Right. Okay, thank you.
Yeah. Any other question? So here I'm just, yeah.
Maybe I have also a question.
Yes,
so
sure.
Did we say why is the area that gives the entropy? Or
yeah, so no, we didn't say why it is the area. We just, it came out of this particular computation, right? Integrating this formula. It looks, I mean, it could have been a more complicated function from, or something else from just integrating this formula. I didn't explain why exactly was the area. Yeah, maybe. Perhaps I could explain why it is the area. So unfortunately, I cannot write, but it would be nice if I, let me try to explain in words. So the entropy is calculated by a derivative of the partition function with respect to the length, to the inverse temperature, right? So that would be like making a variation of this length, okay? But any term in the partition function which is exactly linear in beta will not contribute to the entropy. This will be like the energy term in the partition function, okay? So the entropy somehow is an expression, so it's like 1 minus beta dd beta. So it's a combination that picks out exactly some terms that are not linear in beta. Now, if you look, so the partition function is computed by integrating the Einstein action on this geometry. And the Einstein action is some integral of something which is local, so it's defined everywhere. And so if there are some, when you're integrating over this region, the result you get in the integral will be independent of the size. Well, will be exactly linear in the size of this circle. Okay. But the contribution sort of near the tip do not have this property. And when you try to figure out exactly how that contribution changes, when you vary the size, you get the area. Let me say it in slightly a different way. So if you vary the length here, if you vary the area naively, you would get here a conical singularity. So geometry with a conical singularity. And if you evaluate the action on that geometry, so the integral of the curvature will have a delta function at that point. So that would be one point in this two-dimensional space. But then you have to do the integral over the two sphere. Okay, so that would give you the area. So that's
I see. Okay.
so these are elements in the explanation. So I still haven't given you the full explanation, but these are the basic elements of this explanation.
Thanks.
Yeah, so the formula for the mass, for example, of the black hole depends on the full solution and so on, but the formula for the entropy only depends on the area of the hole. So it's simpler. In some sense, it's formula for the entropy is simpler than the formula for the mass. Okay, so yeah, is there any other question? So now we'll start talking about the geometry of the black holes, including the interior. So if you have a star that collapses into a black hole, the space-time diagram can be represented in this way. So these are some diagrams that are useful to make to represent the geometry. Of course, the geometry is four-dimensional, but what we are going to do is we are going to consider purely spherically symmetric geometries. So we are going to forget about the directions of the sphere, and we are only going to draw the radial and time directions. So there's a radial direction that goes out and the time direction that roughly goes up. And then we are going to rescale. So the radial direction is infinite and the time direction is infinite, but we're going to do a rescaling, an overall rescaling of the metric that brings that infinite geometry to finite region. So these blue regions here are the regions which are at very large times and very large distances. So the far away region of flat space. And the rescaling was done in such a way that light rays move at 45 degrees. So for example, this is the direction of a light ray. Another light ray that comes from the center of the star, goes through the star and goes to infinity would follow this trajectory, and so on. So these are the so-called Penrose diagrams. So done with these rules that I've just tried to explain. Now here, this region here is r equal to 0. That's the center of the star. At this point, the size of the sphere shrinks to 0, but in a completely smooth way. And then the Schwarzschild geometry describes those coordinates that we've discussed describe the geometry in this white region outside the black hole horizon. So r equal to rs is not a point, but is actually this whole line that we call the horizon. And the geometry continues. So that's what happens at r equal to rs is just the coordinate singularity. You can choose some other coordinates where the geometry continues. And there is another region that we call the interior. So the interior region is a region that is time dependent. So it's time dependent in the sense that an observer who goes in here sees that the sphere, for example, is contracting, and it looks a bit like a collapsing universe. It's not completely isotropic, but it's an anisotropic collapsing universe where some directions, like the direction of the sphere, collapse more than, let's say, the other spatial direction. Okay, so that's how the geometry looks like, and this red line, the size of the two sphere shrinks to 0. The details of exactly how the interior looks like or how the singularity looks like depends on what perturbations we have, and it depends on some details. So in the simplest spherically symmetric situation, this is how they look like. But in all cases, there is a horizon, and beyond that, there is an interior with some singularity. Okay, so that's the geometry of a collapsing black hole. It's of course important that so if you are here at the surface of the star, nothing special happens when you cross the horizon, or similarly, if you're falling in, nothing special happens when you cross the horizon. Now, there is an interesting classical property of black holes, which is that if you look at the horizon, or maybe I didn't explain what the horizon was. So the horizon is the following surface. So imagine that you have a light ray that the horizon is a surface that divides the region that can send signals to the exterior, to infinity, from the interior, which cannot send signals. So if you're in the interior and you try to send an outgoing signal, it will start going out, but it will fall into the singularity. Okay. And the horizon is the dividing line between those two. So it's a light ray that if you send the light ray just before that, it can make it to infinity. Just after that, it can go in. And if you are exactly there, the light ray sort of starts going out, but it never really goes out or falls in. Okay. Now, this horizon, this imaginary surfaces, I call them imaginary because if you're an observer who falls in, you don't notice where it is. But so it's a mathematically defined surface, has the property that the area always increases. So in this case, for example, it starts with 0 area here, and the area starts growing as we get to the surface of the star. And then out in this region, the area is constant. So for the Schwarzschild solution, so Schwarzschild solution is a solution in the vacuum. So it only describes the white region here. The green region is described by a different solution. But anyway, so this is the final geometry, and the area increases and then remains constant here. And it turns out that no matter what process you have, the area of horizons always increase. So even if you have something very complicated, like the collision of two black holes, the area of the horizons of the black hole that forms in the end, it will be larger than the area of the two initial horizons. And given that given that the horizon area is associated to an entropy, this classical property of the growth of the area is it can be viewed as enforcing or as a consequence of the second law of thermodynamics. Now, the full entropy of the outside of a black hole is not just purely the area, but it's also the area plus the matter. There might be some entropy of matter outside the black hole. And so the total entropy outside should also include the matter. In fact, Bekenstein actually consider, well, always include the entropy of matter. And then he said, oh, we should also include the area term. But we should always consider a combination like that, which is the total entropy outside the black hole. And this is sometimes called generalized entropy. It's called generalized because it has the area, not just the entropy of matter plus just the area term. Now, one question you can ask is the following. So a black hole emits Hawking radiation, and by doing so, it loses energy. And so its area becomes smaller and smaller. And so one question is, what happens to the entropy? It seems to decrease. However, we should remember that we are including this entropy of matter, and this entropy of matter includes also the entropy of quantum fields. In particular, it will include the entropy of the Hawking radiation. And when you look at the Hawking radiation process, you find that this entropy is increasing because there is Hawking radiation coming out, and the area is decreasing, but the total combination actually increases. Okay, so the entropy of Hawking radiation increases faster than the area decreases, and so the total entropy is increasing, as we expect from the laws of thermodynamics. Okay, so it obeys the second law of thermodynamics. So, but the one.
Sorry, can I ask something there?
Please, yeah.
Yeah, but the second law is that the entropy of the whole universe, I mean, in the sense that
yes.
So the idea here is that the universe is just the black hole, no?
No, well, it's everything that is outside the black hole. So we consider the exterior plus the black hole, and that entropy is increasing.
So all this is contained in this S.
Yeah, it's the S matter.
Okay.
So you have some S matter, so there might be some entropy very far away that does nothing, but we are considering, but S matter will increase due to the emission of Hawking radiation.
Okay, okay, thank you.
And the area would decrease. And yeah, and when the black hole initially formed, this entropy outside increased by a big amount, which was because of the area increased rapidly. Okay. So during the formation process, maybe I should have emphasized that here. So if you are some observer looking at the black hole from the outside, the black hole forms relatively quickly within a light crossing time of the within a Schwarzschild radius. And in that time, the area increases from 0 to this large value. Okay. Now these results have given rise. So these results were all essentially found in the 70s, most of them. Only more recently, more issues regarding this, including the quantum fields here and the validity of the second law, including the quantum corrections, for example, in black hole evaporation. Those were proven relatively more recently, like in the 2010s. It was proven in a nice way by Aronwald. Now, all these results have inspired the central hypothesis, or some hypothesis. And this is that black holes can be viewed as quantum systems. So the idea is that if you look at the black hole from the outside, it can be described as a quantum system, which has S degrees of freedom or qubits, where S is the area over 4 g Newton. And not only that, but if you stay outside, it evolves via a unitary evolution, as seen from the outside. So these two properties are not manifest from the Einstein gravity description and from the gravitational results, but those properties of the entropy are viewed as a little bit like evidence that this idea is correct. And I'm trying to spell out this idea because this idea plays an important role in the development of this subject, and trying to understand whether this idea is or is not correct is an interesting area of research in which several of us are working on. And you might have heard some version of this idea, and so I'm trying to spell it out carefully. Sometimes people assume more than what is stated here. So this is, I think, the minimal assumption or some assumption that you could make. And we call it the central hypothesis. Sometimes we also call it the central dogma of black holes. So some hypothesis that you make.
Juan, can I ask something?
Please, yeah.
Maybe it's early, but I will ask it anyway.
Yeah, please.
So what is the quantum character of these degrees of freedom? So what is the quantum state of?
Well, yeah. So this does not specify the Hamiltonian. It only says that there is some Hamiltonian. Okay? And so it says two non-trivial things. One is that the number of degrees of freedom is finite, it's not infinite, and it's roughly given by the area. So that's one non-trivial thing. The fact that they are qubits and not interact, you shouldn't view them as non-interacting qubits. They are very strongly interacting. So it's just, this is just telling you what the dimensionality of the Hilbert space, which should be e to the s, right? And the second point it's making is that when time progresses, there is some Hamiltonian that we don't know that makes them evolve in a unitary way. So there is no information loss. The evolution is not just that of an open system, right? So you might, so let me try to contrast this with some other idea you could have had, right? So another possibility is that maybe indeed there are this number of degrees of freedom, but then there is the black hole interior and information is lost by going into the black hole interior. And so then the evolution would not be unitary. Right. So there is some, and this is a perfectly reasonable other hypothesis you might make. If you make this other hypothesis, then there is no reason why the second law should hold, for example. So it could be that the entropy is lost to this other system, and there is no reason why the system you have, which is the outside, should obey the second law. So like if you are in a room and you know, the air leaves the room, the entropy of air inside the room could decrease. So I view already the results of the 70s, this increase of the second law and so on, as evidence, if you wish, for this hypothesis versus the alternative hypothesis, which is that. But well, this is debatable, and some people might reasonably say that, well, they don't like this, or the evidence for this is not complete, and so on. In the course of this talk, we'll see more evidence for this point of view, but you should feel free not to believe this. So this is certainly not something that is not a theorem. It's just some assumption, and we're trying to figure out whether the assumption is correct or not.
Another naive question here.
Yes.
So could you please go one slide back, because maybe I'm too slow on this, but in the previous slide you had the entropy. No, one more here. Yeah. So I'm trying to think of this entropy on the left during the collapse, where you don't have a black hole yet. So the radius of the star is still larger than the Schwarzschild radius.
Yes.
The first term on the right then will be 0. The area is not there because there is no black hole yet.
Exactly. Yeah.
We only have the S matter, and then suddenly we cross the horizon, and as you say many times, nothing special happens there. It's a well-defined mathematical region, but nothing happens there. But suddenly, now the entropy has two components: has the area term, and the S matter.
Yes.
So I'm wondering, how is it this transition happens? How is it you have an entropy that goes like the volume, and then suddenly you have two terms, then the one's got the volume, one with the area?
Yes. Well, it's important that the observer for whom nothing happens at the horizon is the one traveling with the star that goes into the interior. Okay, that's one observer. Then the observer that is computing this entropy is an observer who's sitting outside the black hole. So all these entropies that we are going to talk about now are entropies for the black hole as seen from the outside. So you are going to stay outside the black hole and do, let's say, experiments or measurements outside the black hole. So so from the outside, it's a calculation. I mean, you calculate that that there is a horizon that forms. There is some region of space-time you can see. You mathematically think it exists, but it's not visible to you. And it's like the cosmological horizon, right? So the space presumably continues, but we can only see up to a certain point.
Okay.
Yeah, and we should include the area of that when we calculate the entropy. That's the idea.
Okay.
And so that's but notice this we are calling this an entropy, but this is the result of some, let's say, geometric computations like the Euclidean black hole computation. And it's again a hypothesis that this is the entropy of some concrete quantum system. And so here, the first part is that the area can be interpreted as an entropy. That's another way to state the first hypothesis here, that that area is really an entropy of some concrete, quantum system. It's not something.
Okay, thank you.
That the area, the area contribution is really an entropy. Okay, so in some other ways, so the idea is that we look at the black hole from the outside. Let's say we take the black hole, we see it, let's say, outside a certain radius, which is bigger than the Schwarzschild radius. And then we replace the black hole by some quantum system. So the idea is that if we are only going to stay outside this dotted line, never get any closer, but we can send fields and receive fields out of the black hole, particles, and so on. Then we can replace whatever is inside this dotted line by some system of qubits, some complicated system. Some call it mysterious because we don't know what the Hamiltonian is in general. But yeah. So in particular, well, as I just mentioned, so when we do this computation of the Euclidean thermodynamics, we are doing some gravitational computation, and geometric computation, and this central hypothesis is telling us that that computation could be interpreted as a trace of e to the minus beta h, where h is that mysterious Hamiltonian. Okay, so the concrete calculation we do in gravity involves the Einstein action and fields propagating on this background and so on, and we can compute this right-hand side. This left-hand side and this Hamiltonian are some hypothesis that is something that should exist, and we can wonder whether the results we get from the right-hand side are consistent with the idea of this being a trace. So for example, we couldn't get that this right-hand side gives us something negative, for example, and it does. Now, there is some evidence for this hypothesis by now, and the evidence is, well, there are different calculations. So the first one is the entropy counting. So there are some special black holes in special theories, some supersymmetric theories that can be described via string theory. And using strings and some objects that exist in string theory, you can give a counting of the states, and that reproduces the area formula. And not only the area formula, but also the corrections to the area formula that include that matter entropy term that we were discussing, and some other further terms that I'm not talking about. So that's one aspect. The second is by this ADS-CFT conjecture, which is the idea that if you have physics in an anti-de Sitter space, it can be described by a conformal field theory on the boundary. Then in that case, you are replacing not only the black hole, but the whole spacetime around the black hole by a theory that lives on the boundary, and the theory lives in the boundary, has a concrete Hamiltonian, and has it's a unitary theory. Okay, but well, so if you believe this conjecture, then you would conclude that hypothesis is true, at least for black holes in ADS. And not only include that, but it gives you it tells you what this hypothetical Hamiltonian is in those cases. Okay, so these are some evidence for it. You might not like it, but there is also some evidence against this. So Hawking in 1976 was motivated by this hypothesis that was already being discussed then, and tried to argue that this could not possibly be true. So Hawking's argument relies on looking at the geometry of an evaporating black hole. So this is similar to the geometry that we discussed before. So before we had this region where we formed the black hole, and now we're going to include the Hawking radiation. And if the black hole, let's say it's evaporating, and then it will shrink eventually. And we're going to make the mild hypothesis that when it shrinks, it disappears completely, and we end up with flat space in the future. Much of what I say does not depend on that, but just to draw this diagram. Now, the point is that in the far future, we'll end up with flat space with some radiation coming out. Okay, that's what this arrow is saying. And this geometry here in the future is that of flat space. This is the r = 0 point. And then the process of Hawking radiation involves creating pairs of particles, entangled pair. It's important that these particles are entangled with each other. So there is one member of the pair goes into a singularity, and the other member of the pair goes to the radiation. And when we only look at the radiation, the quantum state of the radiation looks as if it is mixed. So it's mixed because we are not observing the partner of each of the modes, which is entangled with it. And there is a non-trivial entanglement entropy, and so the state looks mixed for the radiation. Okay, so the
When-
state, yeah.
Can I ask a quick question?
Please, yeah.
Are there any computations in some toy model like string theory?
Yeah.
In which you can actually see the black hole evaporating completely and just getting Minkowski space afterwards?
Well, it depends on, there is no model where we have an explicit description of this final point from the geometric point of view. If you believe this type of descriptions, so here you assume the duality is correct, then you could couple this field theory to some external bath system, and then it will lose energy, it will decay to its ground state. And the ground state is supposed to be the system without black hole. But this is not telling you exactly how that happens.
Okay, thank you.
Yeah. In fact, the last paper I wrote was related to small black holes. So what happens with small black holes in string theory? But yeah, so the precise mechanism where how that happens is not known. There is sort of a qualitative picture of what happens, which is that a small black hole in the context of string theory should become a highly excited string. And this seems quite plausible. And consistent with some formulas, but the details of, so string theory is somewhat complicated, and we don't understand it well enough to describe that transition, how that transition happens.
Got it.
Okay.
Thank you.
But what's important is that by that time, the black hole has very little entropy. So whatever happens, you could say, well, it cannot solve some of the problems we're going to discuss. So you can phrase many of the problems. You will see in a second that there is a problem that arises before the final time. So in fact, in this transparency. So just to understand better this issue that Hawking was discussing, one can compute the entropy of the outgoing radiation, right? And this will be given here in green. So as a function of time, this entropy rises because we are emitting radiation, it has some entropy, and it reaches some maximum when the black hole evaporated completely. It's not a straight line as a function of time, but it is a monotonically increasing function, okay? Some function that always increases. On the other hand, the thermodynamic entropy of the black hole, so that essentially given by this area term, is also monotonically decreasing because the black hole is becoming smaller and smaller, and eventually it goes to zero, okay? Now, Don Page realized that the problem with this central hypothesis we talked about does not come when the black hole evaporates completely. In fact, comes earlier. It comes when the black hole evaporated enough so that the entropy of the radiation becomes comparable to the entropy of the remaining black hole, okay? So why is that? So imagine that you form the black hole from a very low entropy state, let's say let's say, yeah, so from a very low entropy state, it could be a star, and the entropy of the star is negligible compared to the entropy of the black hole. But anyway, so you form that, and now the entropy of the radiation starts going up, but that could be fine because that radiation could be entangled with the degrees of freedom of that we're describing the black hole initially, right? However, you have a problem at this point because I mean, this initial rise of the entropy also happens if you are burning a piece of paper or a piece of coal that starts in a simple state, and then you emit radiation, the entropy of the radiation increases, and the quantum state of the radiation is entangled with the remaining piece of paper. But at this point here, if we have a unitary system, then yeah, so there is a problem. And the problem is the following. So suppose you are at this point where the entropy of the radiation is bigger than the thermodynamic entropy of the black hole is the total number of degrees of freedom remaining in the black hole. And so it cannot possibly be that these entropies are rising from entanglement with these remaining degrees of freedom. There is some entropy production in it somewhere, right? It didn't arise because we divided the system into two parts. So there's a problem at this point, and indeed, if we had a unitary system, like a piece of paper that is burning or something like this, then the entropy of radiation should start decreasing at this point. So at this point, we expect that the entropy should follow this blue or purple curve going down, and which is called the Page curve. So Don Page was the one who pointed this out. Now, there were some other apparent paradoxes with the entropy formula. Maybe I won't discuss them too much because I'm running out of time. And we'll.
Sorry, can I ask a question?
Yeah.
Yeah, sorry. So first, concerning this area law entropy.
Yeah.
So is it actually the microscopic picture of that area equal entropy? Is it derived in any case other than extremal black holes?
Yes, so it's derived also for black holes in anti-zeta space, which are not extremal, so at finite temperature.
Okay.
For example.
And the black hole is emitting Hawking radiation?
Yes. So in these anti-zeta spaces, the Hawking radiation comes out of the black hole and gets reflected from the boundary, goes back into the black hole, and it's a system in thermal equilibrium.
So so during equilibrium, then we get this area law, right?
Yes. I mean, that's when you can. I mean, there are some simple cases where you can compute it, and this idea is that you can compute it from the explicit Hamiltonian of the system.
Because what always puzzles me is the problem of negative energy particles inside the black hole.
Yes.
If you allow for negative energy particles, then it's very obvious. It seems, at least to me, that it's very obvious that a negative energy particle will increase the entropy inside the black hole while decreasing its mass, therefore decreasing its area. So it seems to me like it's directly inconsistent with the area law. I mean, the fact that negative energy particles are allowed inside the black hole directly does not allow for area law to be.
Yes. Well, I think well, that's related to some other puzzles that I was going to mention, but so you can have behind the black hole horizon, you can put lots of entropy, lots of matter entropy. You can put lots and lots of particles which have an entropy much bigger than the area. Okay. So that was a problem, and we'll see how this problem will be. That's an apparent problem. It's not a problem if you stick to the definitions I gave before. So in this situation, you will find the horizon, and the statement we made so far is that the entropy for someone who's looking at the system from the outside will be the area. Okay, will not include all this matter entropy. That's the statement we made so far. Now you might say, well, how is it consistent? But we'll see.
Okay, thanks.
Yeah. So these confusions. So most of these confusions involve the black hole interior. So when we try to discuss both somehow this exterior picture and interior, and some of these computations involve the notion of fine-grained entropy, not the thermodynamic entropy, and many of these confusions involve entanglement. So let's go back to basics to that. Yes.
Yeah, I have a question.
Yes.
So as the black hole keeps evaporating by emitting Hawking radiation, there will be a point where the black hole does not have the threshold mass, right, to be a black hole anymore.
Yes, that's the endpoint. So when it gets to the Planck scale, the Planck mass.
Okay.
Yeah. But as we were saying before, the problem with unitarity doesn't arise here at the very end, but arises when the black hole is a fraction of its initial size. Okay. Exactly which fraction depends on the relationship between mass and entropy, but let's say half. Maybe it's
okay.
Okay.
Yeah, thanks.
So when gravity is still valid. Now, this hypothesis was only making a statement about the the black hole as seen from the outside. So it's only when we ask questions involving the outside that we can use this picture. So no statement has been made about the inside yet. Okay. Let me pass through this. So let's discuss the fine-grained entropy. So there are two notions of entropy that we ordinarily use in physics, and it's important to distinguish them. So one is the entropy that appears in the second law of thermodynamics, or sometimes called also Boltzmann entropy, the one that obeys his H theorem. So that's probably familiar from thermodynamics. I won't explain the details. And then there is the fine-grained entropy, or von Neumann entropy, which remains constant under unitary evolution. And so if you have some density matrix rho that describes the quantum system, you can compute trace rho log rho, and that entropy remains constant under isolated time evolution. This is called fine-grained because sometimes if you forget about some details or you're not looking at all observables, then you can define this other more cross-grained entropy formula, which could indeed increase. So let me just, well, is that notion clear, or is the fact that these are two different entropies clear? Or, well, okay, I won't explain it anymore, but it's important that we are going to start distinguishing between these two. And so we're always going to be talking about the entropy of the black hole as seen from the outside, and we could either compute the fine-grained entropy or the coarse-grained entropy. And it's important that the horizon area computes the thermodynamic or coarse-grained entropy or Boltzmann entropy. And that's because when the black hole forms, it rises very quickly, while if the fine-grained entropy and their unitary evolution cannot rise. Okay. Now, the interesting point is that there is a formula for the fine-grained gravitational entropy that was initially developed by Ryu Takayanagi and then developed by several other people. And this formula says that the entropy involves also a generalized entropy-like formula, which involves the area of some surface. And the difference is that it's not the area of the horizon, but it's the area that results from a certain minimization process. I won't discuss all the details, but well, maybe I will need to discuss some details. So the idea is the following. So you have the black hole, and you imagine, let's say, some initial area of some surface that surrounds the black hole. And you compute the entropy outside this area, this surface, and also the area of the surface. So you compute that quantity. And now you vary the surface. So you got some number, now you make it a little smaller, maybe you get a smaller number, and so on. And you can take this area into the interior, okay? And depending on the geometry of the interior, you'll get different answers for the minimum, for that minimal entropy. So for example, let's consider the black hole that is formed from collapse, right? So that picture of the area that I was showing before will look like a point in this diagram because there are two dimensions that I'm not drawing. And this is some surface in space, and let's say at some moment in time. And we can compute the entropy outside here plus the area here. And in this particular case, we can minimize this by taking this surface and taking it all the way to r equal to 0, where the area term disappears. And all we have is some entropy term. So we compute the entropy on this spatial slice. And that entropy is equal to the entropy of the initial star. So after the black hole forms, this formula gives us that the actual entropy is fine-grained entropy, is the entropy of the matter that made the star. Okay, exactly as we expected for the fine-grained entropy of a unitary system. On the other hand, the coarse-grained entropy has grown. That's the area of the horizon has become very large. Okay. Now there is a similar situation. Well, the situation is different for the full Schwarzschild solution, which has this space-time geometry. I didn't explain in detail. Hopefully, some of you might have seen it. In this particular case, the minimum area is at this point, and we get a non-zero answer for the fine-grained entropy, so for the entropy of just one side. And there are some intermediate cases where we get some results in between. Now, you should be somewhat surprised by the claim that there is a formula for the fine-grained entropy, because in ordinary physics, we don't have a formula for the fine-grained entropy. It's a very complicated thing to calculate. So if you have some gas, let's say in a box, and maybe it could be in a pure state, but if it is a generic pure state, it will be very hard for you to realize that it is in a generic pure state. So there is no simple way to calculate it, but here there is some simple way to calculate it. So these gravitational systems are special. Now this notion of this formula for the entropy also has an associated notion of the so-called entanglement wedge, which is we keep track of the region swept by the surface as we try to extremize the entropy. So we start from this, let's say, cutoff surface that we had surrounding the black hole, and we start moving the area in, and we keep track of this whole region, and that's what we, for historical reasons, is called the entanglement wedge. So in this case of the wormhole, for example, when we went all the way here, we get this line and everything that can be determined by, or the whole region of space-time that can be determined by initial data on this line. So it's a covariant notion. In the case of the interior of the black hole, we go all the way to the center, and everything that can be determined from this slice is this whole green region. Okay. Now we saw that there was a quantum system that described the black hole as seen from the outside. So you can wonder how much of the spacetime does this quantum system describe? It could be just the outside or the portion of the inside, and which portion. And so there is this hypothesis that says that the quantum system describes everything that is included in the entanglement wedge. And by describing it means that we can recover the state of a probe qubit. So if you send one extra qubit inside this region, if you have access to the outside system, you can recover this information. So this is non-trivial because this probe qubit could be inside the black hole horizon. But the idea is that we can do very complex measurements. It sometimes might involve very complex measurements, like running time backwards and even more complicated than that. And in that, this is what, yeah, that's what you might need to do to recover those qubits. So in other words, if you do simple observations, you can see only up to outside the horizon. But what we're saying is that if you do very, very complicated observations of very complicated processes, observational processes, you could see everything that is outside that minimal surface that we discussed before. So everything that is in the so-called entanglement wedge. So this removes some apparent paradoxes, like, for example, these bags of golds that you were asking me about. So the idea, for example, if you have a system which has a big interior but little entropy, then we could describe it, we could describe this whole region. On the other hand, if you have a situation where you have a lot of entropy inside, then this minimal surface that we were discussing would be at the black hole horizon. And the quantum degrees of freedom that describe the black hole as seen from the outside only describe this portion of the space-time. They don't include the rest of the space-time. Okay. Okay. Mm-hmm. Now we can apply these formulas for the old evaporating black hole. And now it turns out that the geometry, so we look back at the geometry for the old evaporating black hole, and let's look at this particular time slice. So time slice that is this orange time slice. And the geometry of this slice is somewhat similar to those bags of golds that we were discussing before, or it's a situation where when at late times, this area could be relatively small. But here inside, you have all the partners of Hawking radiation, and they could have a huge entropy, okay? Some entropy which is much bigger than the area. So that's very similar to the question I was asked about the negative energy particles. Indeed, the partners of Hawking radiation have negative energy, and we can indeed produce a state with a lot of entropy bigger than the area. And in fact, the natural evolution of the black hole, just the process of Hawking evaporation, produces such a state. So that question was highly relevant. And it's indeed the situation we find ourselves in when we have a black hole that has evaporated for a long time. In particular, for a black hole that has evaporated past the page time, we have a situation where the entropy of the Hawking, the interior partners, which is actually equal to the entropy of the exterior because they're entangled with each other initially in a pure state. So that entropy will be bigger than the area of the horizon. Okay. So now if we try to, let's try to use the actual formula for the fine-grained entropy of the old evaporating black hole. So the original formula would tell us, would say, well, find the area which is find the area which makes this entropy minimal. And it turns out that one possibility is one extremum of that functional is to get it all the way to here to 0, in which case it will include this entropy and will be bigger than the area. However, the recent progress was spurred by a very interesting pair of papers, one by Pennington and the other one by these 4 authors, Almeri, Engelhardt, Maroff, and Maxfield, where they realized that there was actually another extremal surface, which is just right behind the horizon. And you can, so it's some work to find that This is an actual extremal surface, minimizing both the area plus the entropy outside. And the interesting aspect about this is that, well, first of all, it has an entropy less than the one I showed you before, and it's an entropy which is equal or of order the area, so similar to the area. Okay, so that's the entropy we would expect for the system. So for the degrees of freedom that describe the black hole from the outside, it's an entropy which is not bigger than the area, so that's good. And in particular, it's leaving out this whole interior here. So it's only that means that those degrees of freedom only describe are supposed to describe only this region. Now, so then we've argued that for a black hole, the entropy of a black hole sort of increases because of the partners of Hawking radiation, and then decreases because we have this new extremal surface. Now, what about the entropy of the radiation? Now, the entropy of the radiation appears to be in a mixed state because it was entangled with the fields that were inside the black hole. And we know this because we calculated using gravitational evolution. Now, this radiation might be in a system where gravity is not important. You might have collected it in a quantum computer and so on. But because you calculated this using the gravitational evolution, we should also use the gravity rules, or these particular rules, that the rules for the fine-grained gravitational entropy, to compute that fine-grained entropy. Okay. So the radiation system, yeah.
Just a question. This radiation is counted in this S matter, right? Or S?
Yes. It is counted. So now what we're going to do is we're going to say, well, let's say we had this imaginary cutoff surface that was separating the region near the black hole from the region far away. Right?
Okay.
Now we're looking at the region far away, and we are computing the entropy of radiation in this whole region. We get a very large number. Okay. So that's the naive calculation of the entropy of the radiation. That's the calculation that Hawking made, and that's the calculation that leads to some puzzle. Okay. But now the gravitational entropy formula tells us that we should try to minimize this. And so one way to minimize it is to also include this whole region of space-time plus the area. So we pay some price, which is this area, but we gain gain something from including the partners of Hawking radiation. And what we gain is that if we have both the radiation and its partner, it does not contribute to the entropy, so we lower the matter entropy. Okay, so we are just computing the entropy now in a bigger region that includes this whole region of the interior plus the radiation. And well, this surface is the extremal surface, the same extremal surface essentially that the previous authors, the authors I mentioned, have found. And now the result that we'll get is that because we're including both the radiation and its partner, that part of the matter entropy does not contribute much, but the area term does contribute, and it will be an area similar to the area of the black hole. So the idea is that these gravitational entropy formulas should include what can be called islands, right? So before, when we were trying to minimize the area, we included everything that was connected. So we started from the outside and we started moving the area, okay, and try to find the minimum. But now we allow something else, which is that we pop out a little island. We include that area and the matter entropy in this island. And if that minimizes, then if that reduces the overall entropy, then we also include it. So in this case, the idea is that we have to include it. And this is just a small variation of the previous formula. It's just that we should include this type of configurations. Now you can wonder where this is just an accounting trick, that we're just counting the entropy differently so that we are solving the problem. But this accounting rule is just the rule that gravity instructs us to use. And not only that, but this accounting rule was derived before it was applied to this problem. And so I'm not describing you the history, but this formula for the entropy was derived by thinking about AdS-CFT and various things about AdS-CFT, and then it was applied to this problem. So it wasn't invented to solve this problem. I'm not going to talk about some derivation of why that formula is correct. So the formula, even though, so the fact that we should include the interior region Okay, here I presented it as a prescription. So here everything hinged on this prescription for minimizing the area and so on, right? But this I just presented as a rule that came from nowhere. Okay, there was no calculation. But there is a way to argue this rule, which is similar to how Gibbons and Hawking argued for the black hole entropy. And I ran out of time to explain how that works, but it also involves doing the gravitational path integral and considering interesting topologies that join the outside to the inside. And if you do all that, then you derive that, that entropy formula. That was done in these papers. Okay. So in conclusions, we reviewed the thermodynamic black hole entropy. We also described a different formula for the fine-grained gravitational entropy. And then we applied it to the computation of the fine-grained entropy of radiation and found that there was no problem. Now, a lot of what we discussed was originally derived and understood by thinking about aspects of ADS-CFT, which itself involves some string theory. But you don't need ADS-CFT or string theory to understand the formulas I've discussed today. You only need gravity as an effective field theory to discuss these formulas. So just the ordinary Einstein theory coupled to matter. That's all you need to discuss the formulas we discussed today. And it's really amazing how gravity contains all this information. It's quite surprising. So in the future, I mean, there are some questions that this has answered. In particular, what the entropy of Hawking radiation is. You can now have a formula and calculate it, and it's a result different from what Hawking had. But there are other questions which this has not yet answered. For example, we would like to have a more explicit picture for the macrostates, those quantum states that contribute to the entropy. We like to have a description for them. We would like to be able to describe them directly in the gravity theory. And we also would like to understand what further lessons this is teaching us about the black hole interior, in particular about the singularity and how the singularity is resolved. So those questions were not answered. So the main question that was answered, just to recapitulate, is the calculation of the entropy of Hawking radiation. Thank you.
Thank you, Juan. Thank you for your wonderful talk. I see that we have time for questions, and I'm seeing that Ali has one, so please go ahead.
Okay, thank you. Thanks a lot, Juan, for the great talk. So I have two questions. The first one is, I have read all the computations, the derivations. I understand the technical way of getting there, but what I don't understand is how is this fundamentally different from just in 1976, including the inside modes with the entropy of the outside the radiation.
Right. So so in 1976, people would say that including the outside modes is just somehow wrong because the observer outside does not have access to the inside modes, right?
Okay.
So that's one thing.
Okay.
Let me. Yeah, you could say, well, now it's also not proven that we have access, so you could counter that. So what's different now is that we can derive the formula by following the rules of the gravitational path integral, right? So you can say, well, I want to compute the entropy, right? Maybe I didn't discuss it. Maybe I should discuss it a little bit. So if I want to compute the entropy, right, we can use the gravitational path integral to compute the entropy. And that is done as follows. So you take n copies of the system, okay, of your state, and then you compute these quantities, trace of rho to the n. So that can be done by taking those n copies and gluing them to each other in some particular way.
Yeah.
And then you can calculate the entropy by some analytic continuation, this index n, and that reproduces this formula for the area and so on that we discussed, the formula that we have to minimize the area. So it's very similar to what we discussed for the black hole. And when this n is like the size of the system, and when you take n close to 1, you have a conical singularity. And this conical singularity is similar to what you get if you had a cosmic string. And the minimization of the area is like minimizing the area of that cosmic string, of that surface. So I mean, that it becomes equivalent to minimizing the action, because we are supposed to be solving the equations, the classical equations. That implies we are minimizing this area. So that's how the derivation goes. It's a generalization of the arguments that Gibbons and Hawking made, and it's the straightforward calculation of the entropy following the gravitational rules. So there is nothing mysterious in some sense. Everything follows from the gravitational rules, and the result is surprising. So because the result is saying that you have to include the interior, so that the interior entropy should be included in the way that we discussed. So that's the result of a calculation. It's not something you put in a priori. So it's just simply the result of calculating the entropy of the radiation following just the rules of gravitational path integral.
Okay, so
let me tell you one essential point that is important for this.
Okay.
So we're going to discuss that case of n equal to 2 when we have two copies of the system. Okay. Now here we are. So we have two copies. So we have two black holes. Let's say a finite temperature, and we are computing the entropy of some radiation outside. And so the outside is non-gravitational, and we fix its geometry. But the inside is a gravitational system that we should be able to connect in any way that we please. So the calculation that gives Hawking's result, we have two separate black holes and two separate, if you wish, given Hawking solutions for each of these two universes. Well, what we are saying is that we should connect these two interiors also in some way. And once we connect the interiors, then the calculations end up including effectively the matter in the interior in the calculation of the entropy. Well, I could explain it a little more if
I would appreciate that.
Yeah. Okay.
Thank you.
So okay, so let me be more slow. So what we do is we apply the so-called replica trick, which involves computing as an intermediate, as a first step, computing this type of quantities. So rho is the density matrix of the system we're interested in, and we take trace of rho to the n. Okay, so we're going to discuss now the n equal to 2 case, just to give you a flavor of how that goes. We are interested in computing the entropy, let's say, outside a black hole. Okay. So we had two copies. Now, rho is defined by is a state that lives in the radiation region, so these wiggly lines regions, so these two regions. And we are going to trace out the rest of the system, okay? Tracing out means that we take the state, the bra and the ket. We can think of the bra as something that we got by Euclidean evolution. Let's say Euclidean evolution goes this way. So we got this way to, let's say, some t equal to 0 slice, which is here, right? And so that gives the bra, and then the ket is another Euclidean evolution that comes all the way to here. Okay. Now we could also mix in Lorentzian evolution, but that's essential. This is the same. So tracing out the region we are not observing is equivalent to gluing the evolution, the spacetime that we got from the bra and the ket, and here it appears as continuous. There is nothing funny happening in this region. Okay. But we got the state that is defined on both sides of this little cut. Okay, so these are the two indices of the density matrix. Is the state on one side of the cut and the state on the other side of the cut. So that's rho, that defines rho, which is just its bottom calculation. And there is a similar rho that we define in the top. And when we take the trace, we are just joining the one part of the cut here with the part in the bottom, and similarly on the other side of the cut. So the net result of that is that if we come in here on this side, we emerge here on the other side. That's how we are contracting the indices in that density matrix. Is equivalent to doing that. And similarly here, if we come in from the top, we end up here on the bottom. So this whole, the path integral, gravitational path integral on this geometry is computed for us that trace of rho squared. Okay. And that's how Hawking would also have computed it. And here in the interior, we have, let's say, these black holes at more or less finite temperature, so they are not connected. Now, a crucial feature of gravity is that we should sum over all possible topologies. So when we do the gravitational path integral, the metric is dynamical, and not only that, but also the topology of spacetime should be viewed as dynamical. And then then we can connect the interior, also the region. This ends up being a region which is inside the black hole. We can just connect these two regions, and we have the freedom to connect them. So here, when we were tracing out the rest of the system, we said, okay, yeah, we trace out also the interior, but the interior we are free to connect it in any way we want among the different copies. And by connecting the interior between one copy and the other, we get this new result. Now, in order to, so this, for the case of n equal to 2, this gives us a geometry which is quite different from the black hole geometry. So it's a big perturbation to the geometry to have this other new topology. But for large times and in the setup that's involved in the page curve, this topology here on the right hand side is the one that actually dominates. It gives the biggest value for the partition function for trace of rho squared. Okay, now when you start going to the n equal to 1 limit, then each of these endpoints becomes a little sort of conical singularity. And that will happen also for, so here in the interior also, if you have several n's, there will be points here where again, you will have a rather small conical singularity when n is small, okay? When n is close to 1, sorry. When n is close to 1, you will be a small conical singularity, and the geometry will be very similar to the geometry of the black hole. And that's how we get this area formula. But the fact that we should be including the interior, and not only that, but the state of the quantum fields will be the state that we had in the original unperturbed geometry. So some part of the magic of these formulas is that we are including some of these effects from other topologies, but the final formula for the entropy includes the original topology. It's just a modified calculation in the original topology. And that includes the effects of the other topologies. I don't know if that was more clear.
Okay, yes, thanks a lot.
So I see that we have Francisco and Javier. First, Francisco, then Javier can ask the question. Go ahead.
Okay, thank you very much, Juan, again. I have two questions. First, what is your view on this proposal from a few years ago from Strominger, Hawking, and Perry, of that the soft hair could account for the entropy of the black hole? And the second question, maybe I can say it right away. This idea of from SYK and being dual to JT gravity of that smooth geometry emerging from this ensemble of quantum systems, how likely do you think that could be extended to to more general situations in higher dimensions, for example?
Oh, okay, so regarding the first question, so this soft hair and the importance of soft modes is relevant in 4 dimensions. Okay, if you are in higher dimensions or you are in anti-de Sitter, then that's not so relevant. And I would expect that a satisfactory explanation of black hole entropy should involve should be valid in any kind of spacetime that we that we can imagine. So both ADS, both lower dimensions, higher dimensions, or whatever. And so the soft modes to me look like some additional complication that we have in 4D, that the dynamics at long distances is more complicated. So that's the answer to your first question. The second question was regarding SYK and near extrema black holes. So the SYK model is a model of interacting qubits, or actually Majorana fermions. but that is relatively simple. So it somehow sits at the nice spot where it's simple enough that you can do some analytic computations and even some numerical computations, but complicated enough to give some physics somewhat resembling those of black holes. And that the model has a kind of, it has a symmetry and a symmetry breaking pattern that is the same as the one we find in near extremal black holes. Now those are the similarities. Some details are different, but it's particularly useful, I would say, for describing near extremal black holes, and it's been, useful for understanding some aspects of near extremal black holes and for understanding the perhaps one of the nicest features is that the dynamics of the quantum gravity, or there's some quantum gravitational effect that that has a simple description for near extremal black holes, and the dynamics of that aspect of quantum gravity is the same both in SYK and in general. So let me just say it a little in more detail. So if you are considering a near extremal black hole, the geometry develops a near horizon region, which is ADS2, so two-dimensional anti-de space, and that space has some symmetries. Okay, those symmetries mean that many quantum gravity corrections will respect the symmetry. But there is one particular quantum gravity correction that does not respect the symmetry and becomes important at very low energy. So energies very close to extremality, it becomes important. And it's that particular single mode that has a very simple dynamics, and the SYK model also separately has a mode with the same action and the same physics, and you can so everything that involves this mode matches the two sides. That's so. Of course, it's very useful to have toy models, and the SYK you can view it as a toy model for near extremal black holes. Perhaps I should say which properties of the near extremal black hole it does not satisfy. So the near extremal black hole has some physics that is local in the bulk. So there is some bulk space, and there's a local bulk Lagrangian that describes fields propagating in that two-dimensional space and or the four-dimensional space, and that cannot be seen. So the SYK model has a more complicated description.
All right. Thank you.
Yeah.
Okay. Javier, go ahead.
Hello. Do you hear me? I'm using a new headphone.
Yes.
Okay. I think it's a basic question, but when you show the entropy, you show that it's the sum of two terms. The first provided by the area, and the second by the matter. And I have the question that which is the limit to take the matter? I think is surrounding the black holes, because I think that if I choose a small portion of matter around the black hole, this term of entropy could decrease and not increase like you talked to us.
Yeah.
This is.
Well, I think let me see if I. So in these discussions, I was imagining surrounding the black hole by some cutoff surface. Let's see. Let me go back here. Okay, so you have different options. So let me preface it this way. So you have the option of how much to include about the exterior, right? So you can decide that you include. So there are two surfaces in the discussion, let's say. Well, let me first discuss the simplest version. So we could discuss including the whole exterior, right? the whole exterior of the black hole. That would include all the matter that is outside the black hole, even very far away, and so on. And then we're talking about the surface we minimize is some surface which could go into the black hole interior. Okay. So is that, do you have your question about that, or is your question about something else?
Yes, that's it.
Yeah. So is that setup clear? When we can have the whole exterior?
Yes.
Okay, good. So then your question is about setups where we are not considering the full exterior.
Yes, because I think
yes.
you choose.
Okay, yeah. So when we don't consider the full exterior, what we are doing is basically the following. So we are dividing the exterior into two pieces. So some region that is very far away from the black hole. So we have this imaginary surface that, let's say, surrounds the black hole at some distance from the black hole. You're free to choose this distance. And then we treat the exterior of this region as non-gravitational. Imagine there is no gravity, so we pick here a fixed surface. And now we are going to compute, when we compute, we divide the system into two pieces, the exterior and the interior, and what is inside this surface. So the formulas some of the formulas I was talking about involve the calculation of the entropy within this surface, right? Then we would take so I was drawing I was drawing that in green. Let me see, like in this picture. So we have this this surface that divided into two regions. Now I'm free now to compute the entropy of this region, and for that we can consider this green surface, and we'll start moving this green surface in or out, and trying to minimize it, right? We could, yeah. So that's the rule, okay. Now, if we were compute, and the answer you will get for this entropy will depend on where you put this cutoff surface. So you can put the cutoff surface a little bit further out, and you'll get a different answer. I think that was the question. That is indeed the case. You will get a different answer, but the idea is that in the whole discussion, we just keep that fixed, and then we are asking how these various entropies change as the black hole evolves. So when the black hole is young and just has formed, there is little radiation in this region. When the black hole is older, it has emitted Hawking radiation that has crossed this surface and has gone into this second region. Is the answer clear?
Yes, yes. Okay. Thank you very much.
Okay, let's take the last question. Spiros, go ahead.
All right, it will be short. So is there any simple physical explanation about this area that gives the entropy? Because the horizon, I mean, I understand it is, light can escape or cannot escape.
Yeah,
but
yeah. Well, I think the simplest qualitative explanation is the following. So when you look at the black hole, for example, let's consider the point of view of an observer who sits at fixed radial position, right? So if you're at the fixed radial position, then what you find is that the proper length of your circle here in the time is it gets smaller as you approach the horizon. What that means is that observer will see a higher proper temperature. So the temperature will look higher to you. You will be accelerating more, but you'll see a higher temperature. And then you can, as you get closer and closer, that temperature goes to infinity, right? And one attempt to calculate the entropy is just to calculate the entropy of the quantum fields that are outside the horizon, right? So for example, the photons, let's say, the massless field. And then you just would compute the entropy with this temperature that varies with distance, right? Basically the temperature, this circle here looks like the circle in Euclidean space, essentially. So the proper length goes like 1 over like r, right? And the temperature will go like 1 over r. 1 over r, r is now the distance from the horizon, or 1 over d, where d is the distance from the horizon. So you take a gas of massless particles and whose entropy goes like T cubed, right? and you integrate it in D. So you have 1 over T to the cube, integrate in D, you get something that goes like, well, you'll get an infinity from this, okay? Now, let me first give you, well, if you cut off this infinity at the Planck scale, right, you'll get something that goes like 1 over L Planck squared times some area, because it's you are computing the entropy of this gas. There is some simple volume factor, which is just the area. So that's a qualitative explanation for this. This qualitative explanation is not quantitatively correct because we cannot trust the theory to distances of order L Planck, and the explanation does not give you the precise prefactor. But at least it kind of gives you a vague idea of where the entropy could be coming from.
Okay, and just
the conservative way to explain this, or the more proper way to say this, is that you should choose a cutoff bigger than a distance scale, much bigger than M Planck. Then there is indeed this divergence, and well, it's not diversion. I mean, it's cutoff, but it will go like 1 over the area over the cutoff, and the same in the same framework, you should be putting a cutoff also in the sort of bulk theory of that order, and that gives rise to an induced Newton constant, a correction to the Newton constant that precisely cancels this cutoff, so that the final formula for the area is the original L Planck.
Right. So it does not depend on the cutoff.
Yes, that's right. So that's the way, let's say, the conservative effective field theory way of saying it. But I think that this other slightly not completely correct way to say it still gives at least a qualitative view of the origin, that if we could understand gravity well at the Planck scale, maybe we could understand the entropy that way. Maybe that's one way one could say it.
So just a final comment, would you consider that the information paradox is solved with this discussion?
No, I think there is one aspect of the information paradox has different aspects. So there is one aspect which is the entropy of Hawking radiation. That's been computed and understood how to compute the entropy. But there are other aspects like, for example, if you send something into the black hole, what state comes out of the black hole? That so it's sometimes called the black hole S matrix. That has not been understood. It has not from the gravity point of view. So
I see.
We have some dualities and so on that can allow you to compute it, but we do not understand it directly.
But
from
is
the
this technology also relevant from that for that direction, or it's a completely different problem?
Well, we don't know. We don't know. So this technology, I think in some sense we were lucky that the entropy turned out to be a simple observable. So the point of view now is that there are some observables which are simple enough that we can compute it using gravity, and some other observables which are more complicated that require a more detailed understanding, for example, of the singularity and other properties of gravity that go beyond Einstein gravity or beyond the gravity as an effective field theory. I emphasized at the very end that we could do everything we were discussing using gravity as an effective field theory, but in some sense that's because we were lucky that the observable we were computing can be computed in this way. I mean, people, certainly most people thought that the fine-grained entropy could not be computed in that way. So that's what I thought before. But
yeah.
So it is a surprise that it can be computed using gravity. Now, again, now we think that those S matrices cannot be computed using just gravity. I think they will involve going beyond the gravity as an effective field theory. And, yeah, so that's, I think, well, that's my point of view, but maybe someone in the future will come up with some clever way to do it. I will have to say that. I wish, yeah. So,
cool.
But
Thanks.
In some sense, there is a kind of, this is a double-edged sword somehow, because what we really would like to understand is the singularity, right?
Right.
But if it is computable in gravity, then we will never need to say anything about the singularity. That's why the entropy computation, because it involved this surface that was far away from the singularity, it could be done. And so we are not learning anything about the singularity.
Right.
But it might be that the other observables that are harder to compute are more interesting because they will teach us something about the singularity. I mean, that's what I would hope that is the case. Yeah.
Okay, so unfortunately we are out of time. Well, but let's thanks again, Juan, and thank you everyone for coming today. Have an excellent day or night, depending on where you are in the world right now.
Well,
and hope to see you again in the next seminar.
Okay, great. Yeah, see you.
Thank you,
Bye-bye.
Juan.
Yeah.
Bye, everyone.
Bye-bye.
Bye-bye.
Take care.
Thank you very much, Juan.